Right, gents. We're kind of moving on to the second learning outcome that's in paper 1 of the maths. We're going to spend a couple of weeks on this. Okay, complex numbers. So what we're going to look at today is representing complex numbers in both the polar and the Cartesian, which is a kind of a mathematical term. In engineering, we often talk about rectangular form. So polar and rectangular form, that links in with the way we use the calculators to do this work. Okay. Addition, we're going to look at addition and subtraction of Cartesian complex numbers, multiplication and division of Cartesian complex numbers. Look at multiplication division of polar complex numbers, the use of calculator to convert between the two forms, and I'll put down addition and a subtraction of polar complex numbers, but I'm not going to cover that in too much detail, because what you're going to do is convert it to the other form and then back again to do that one, because to do that the manual way requires you to kind of draw the problem out and have some knowledge of geometry, a bit of a kind of long-winded way around doing something when you've got the modern calculator to help you. Okay, so I'll just briefly look at that, but not spend too much time on it. We'll do it the calculator way. Right, so use of complex numbers in engineering. We have a number of what we'd call, we're going to look at scalar versus vector quantities. Some physical quantities are entirely defined by a numerical value. They're called scalar quantities or scalars. Typical examples: time, mass, temperature, energy, and volume. They can be easily described just by a number. However, other physical quantities, defined by both a numerical value and a direction in space. So to fully define them, you need to define their direction as well. So that's what this complex number stuff is all about for engineers. There are other uses of complex numbers, but for engineers it's mainly about this representation of what's called vector quantities or vectors, things that have got not only a size but a direction. So you can define speed in its scalar form just by saying how fast you're going, but to fully define speed you need to change it to a velocity and say it is a speed in a particular direction, like east or west or northeast. Yep. So examples of vectors include force, velocity, moment, displacement. We could add to that acceleration, because that's got a direction as well. Okay, so if you think you're traveling along in your car at 30 miles an hour, if you're changing direction, you're actually accelerating in that different direction. Although your speed is constant, you're actually accelerating in another direction if you're actually turning at that time. So it's quite a difficult concept to get across at first. Okay, so for engineers, these complex numbers are mainly used to help you describe these kind of quantities that not only have a size but also have a direction. So, first of all, what I want you to do is try using your calculator to evaluate those numbers. So, as Kelsey rightly says, the answer to that is no can do. Can't do it. You get a math error. Let's write that down. And for once, it ain't because you put the numbers in your calculator wrong or anything like that. What does square root mean? What is the answer to the question square root of a number? I do square root of 9, what's the answer to that? 3. You know it's 3, but how would you describe the number 3, the result of the square root of 9? Yeah, it's the number when multiplied by itself equals 9 in this case, in this example. Yep. So what we're saying is the opposite of square root is square. If we do minus 2 times minus 2, what do we get in the calculator? No, this is times. What do we get? Oh. Yeah. So there's no square root of any real square root of any negative number, because if we square a negative number, we end up with a positive number. Yeah. So trying to do that up there does not give us any kind of real result. Our calculator says there's a math error. Okay. So what the mathematicians do, and engineers also do, but do it a little bit different, as they say the math operator j is equal to the square root of minus 1. Okay? Mathematicians say I is equal to the square root of minus 1. Okay? But we, as engineers, we don't do that because that's too much ingrained in. I is used too much. It's used for current in electrical circuits, so it'll be a bit of an issue to use I. So we use the next number, the next letter in the alphabet. Sorry. The engineers use J is equal to the square root of minus 1. Yeah. So what happens there is if we want the square root of let's say we wanted the square root of minus 9, okay, how we actually describe that is minus 9j. Yeah. So you've taken, sorry, not that, j times 9j. What you're doing is effectively 9 times the square root of minus 1, which we call j. Do you see that? Okay, so you're effectively multiplying the number 9 by the square root of minus 1, which we're calling j. I won't get too much hung up on that, because as engineers, what we're really interested in is using the technique to our own means, not the mathematical theory. Okay? I'm going to add another slide. Right. If we say j is equal to the square root of minus 1, what do you reckon j squared is equal to? Exactly, minus 1. Yeah, because you're cancelling out. We've taken this and we're squaring it, which cancels out the square root sign. Yeah? So in that case, what does j cubed equal? Not quite. Minus j. Yeah? No? J squared is minus 1. So it's minus 1 times j. Yeah? Because j squared is minus 1. Yeah? So we got j cubed is j squared times j. Minus 1 times j. Alright? And you can carry on j to the power 4 and so on, but we don't need to. We only need j squared, and j to the power 3 to fully describe any of our angles around the 360 degrees or 2 pi circle, right, which we're now going to look at. So we're interested in the fact that j, to summarise, j is equal to square root of minus 1, j squared is equal to minus 1, and j cubed is equal to minus j. Okay? And that will help to understand as we go on today. So, representing vectors mathematically, this is what we're really interested in as engineers. How can we represent these quantities that have got both a size and a direction? And they can be presented mathematically in two forms. In Cartesian or rectangular form, I'm going to write that on there as engineers. Where we have an imaginary axis and a real axis. And the vector is described in two parts. A real part on the x-axis and an imaginary part on the y-axis. Yeah. So this is the vector we're looking at here, this line up here. And what it has described is, how many is it along? 4. And how many up or down times j? So this is 4 across plus 3j, because there's 3 up. So that vector is represented by the complex number 4 plus 3j in that form. Okay. If we go over into this area here, the x-axis becomes negative. So a similar vector in that direction is minus 4 plus 3j. We come into this quadrant here, and we need to talk about these in first, second, third, and fourth quadrants. It's useful to be able to work out which quadrant the angle is in, to know whether you're getting your answer in the right area. Okay. In the third quadrant, both quantities are negative, both the real and the imaginary part are negative. And then if in the fourth quadrant, the real part becomes positive again, but the imaginary part is negative. Okay. If we look at the just look what I've got on the next slide. That's fine. If we look at a particular complex number, 4 plus 3j, okay, real part, okay, in your bird textbooks, you'll see that he puts the j before the number. I actually prefer to work with putting the j after the number. and I don't really matter, and I don't know why they do that in maths textbook. I prefer to see the J. I think that's easier to not lose it into variables if you put it after the coefficient, personally. So I'm going to stick to that. But your bird maths books put the J first. Okay. You'll also hear this called horizontal component in some terms of the vector, the horizontal component, and this called the vertical component. Okay, and it's about vectors that can be have a direction anywhere around a circular motion that is anti-clockwise. We talk about the angles here being anti-clockwise, starting from 0, going through 90 degrees up there, or pi over 2 radians. And again, with this work, we're going to need to be careful that we've got our calculators either in radians or degrees mode, depending on whether we're working with angles in radians or degrees. Over here, 180 degrees or pi radians. Down here, we can have 270 degrees or minus 90 degrees, which is 3 pi over 2 radians or minus pi over 2 radians, whichever way you want to work. Usually as engineers, we work with angles up to positive 180, angles this way up to a negative 180, rather than dealing with the angles all the way to 360 degrees. Particularly in electrical engineering, that sign gives you the leading and lagging situation that you get in electrical circuits. When we move on to science in semester 2, we'll be doing a little bit about that. Okay? So you will definitely come back to this in my half of science, electrical half of engineering science, and probably will do so with Adrian as well. You look at forces acting in different directions. I don't know what is in the mechanical science in that much detail. So you may well get complex numbers in that as well. Over this side, we're looking at polar representation, where that is represented by the length of the line, the magnitude here, and the angle in between. Yeah. So you represent this vector by, let's say, 5 angle alpha, for instance. So it's represented by the length of the line, an angle between. This one might be 6 angle minus that angle in there. Okay? Yep. I'm just saying it could be. You would describe a vector by the length or the magnitude of the vector, and then say what angle it is around the anti-clockwise 360 degrees. Or you can go down in the bottom half, the bottom 2 quadrants 3 and 4, describe it with a negative angle. Again, either in radians or in degrees. We'll come back to the polar representation in a bit more detail later. Okay, I'm going to major on the rectangular to start with. Right, everyone happy to move on to the next bit? So, if we're going to represent these vectors in this way, we need to be able to do some mathematical operations on them. So the first thing, the easiest thing to do, is addition and subtraction of Cartesian or rectangular complex numbers. Two complex numbers are added, subtracted by adding or subtracting separately two real parts and the two imaginary parts. So a simple case, if Z1 is equal to A plus BJ and Z2 is equal to B plus DJ, we add the two together in this form by simply saying it's A plus C, the two real parts added together, plus B plus D times J. And we must be very careful not to drop that J off the end there. Lose it. Okay? It could end up getting lost. It could end up being 0J, cancelling out. Okay, and we're going to come across a specific case where we want that to happen later on. Okay? You're looking intent, Jake. Is there something? Sorry? Yeah. I said the examples with numbers at the bottom probably help better than anything. Subtraction. The two subtracted is the second real part subtracted from the first plus the second imaginary part subtracted from the first, again times J. Alright? So in the example down the bottom we got 2 plus 3J, and we're going to add to that 3 minus 4J. So we do 2 plus 3 for the two real parts, and we do plus 3J minus 4J for the imaginary parts. We end up with a result of 2 plus 3 is 5, and 3 minus 4 is minus J. Okay? What quadrant is that complex number in? Without looking at the diagram. Yeah, it's got a... sorry. It's got a positive real part and a negative imaginary part. That's in quadrant. It's in here. Yeah, quadrant 4. Okay. If we subtract 3 minus 4J, and you need to be very careful with signs doing this arithmetic. That's 2 minus 3 is minus 1, and that's plus 3 minus 4. So it becomes 7J. And that one is in which quadrant? Minus 1 plus 7J is in quadrant 2. That's up here somewhere. In fact, that's quite steep, really, because we're only minus 1 on the x-axis, 7 on the y-axis, so that's up there like that, something like that. Okay, if we look at the other one a little bit more carefully, 5 minus 1J, that's a vector more like that, over that way, because it's bigger on the x-axis than it is on the J. Yeah? So, simple addition and subtraction is add together all the real parts or subtract the real parts and the imaginary parts separately into one number. Over the old page, just a quick look at the fact that you can do this graphically as well. So if you were to draw a scale diagram of your vectors, so in this case we've got the vector P, which is 2 plus 3J, so we've gone 2 along and 3 up and drawn in a vector, and then we've got 3 minus 4J down here, so we've gone across 3 to the right and down 4, and then we create a parallelogram out of those vectors like so, and the resultant addition of those two vectors can be measured off on the axis, minus j and plus 5. Yeah? So you can solve it graphically. The other thing about graphical is a quick sketch could help you make sure that you've got the signs of your results right. So if the actual result was difficult to read off the graph, a quick sketch will still give you a rough idea of whether your answer's in the right quadrant. Okay? Subtraction via this method requires you to take one of the vectors in a positive direction there. So 2 plus 3, we're going to take away 3 minus 4j. There's the 3 minus 4j vector down there. So minus that must be in the completely opposite direction. So you draw that in. That is minus 3 minus 4j. And then you create a parallelogram out of these two there, and your resultant is up there, which is our minus 1 plus 7j. So for a negative vector, you just draw 180 degrees in the complete opposite direction, then create a parallelogram with that one to subtract two vectors graphically. Okay? If you draw those lines to scale, then you can measure off your result if you so need to. So, have a go at that one. Given that Z1 is equal to 2 plus 4j and Z2 is equal to 3 minus j, do those three additions A, B and C. So for the video, I, Z1 plus Z2, so it's 2 plus 4j plus 3 minus j. Add the two real parts there to make 5. Add the two there, so we've got 4j minus j becomes 3j. Perhaps saying the words combine the two real parts might be better. Look at the signs of them, because the sign here always goes with the number that's after it. So that minus sign is attached to the j, that plus sign is attached to the 3 there. So we've got a 4, we've got 4j, and we're taking one of the j's away. So although we're doing addition, we've got to deal with the signs carefully, alright, separately. Second one here, got 2 minus 3 for the two real parts, become a minus 1, and we've got 4 minus minus 1 becoming 5 for the imaginary parts. And that little diagram there with the two vectors, this one and that one being the negative of this one, so our resultant there we knew should be in the second quadrant, and that is, it's got a negative x part and a positive y part to it. The last one, 3 minus j minus 2 plus 4j. So we do 3 minus 2, 1, minus 1 minus 4, is minus 5j. Yep. And does that work? We've got the vector 3 minus j, so that's down there roughly. We've got the vector 2 plus 4j up there somewhere, but we're taking that away, so we've got to do the minus 2 plus 4j. Yep. And so we've got a vector resultant down here somewhere of 1 minus 5j. So the little diagram can help to see whether we're somewhere in the right place. Where 3 what? That's one of the two vectors that we're, it's part of the question. Z1, Z2, sorry, is 3 minus j. It's that vector there. We've taken 2 plus 4 away from 3 minus j. Where? No, actually, he has got that wrong. If you do that properly, it's got to go like that. I'm just wondering if there's a better way to write these out that'll make this easier. Let's have a look. Let's just, I want to clear this up so that you've got a method that you're happy with to do this and get them right. So I'm going to Z1 plus Z2, as that's equal to 2 plus 4j. I'm going to add to that 3 minus j. Well, I think your best route to this might be to do it this way. Equals. Take the first real number 2, add to it the second real number 3, okay, and then that's plus 4j minus j. And then we simply add these two numbers together to make 5, and 4 minus 1 is that the right answer? Yeah? Plus 3j, yes. Okay, so what, like this? 2 plus 3, and underneath 4 minus 1. Yeah, which is what I've done, effectively. Separated the two halves. Okay? Yeah? B, which is Z1 minus Z2, that's equal to 2 plus 4j minus 3 minus j. Using what's gone before that Paul obviously found helpful, that's 2 minus 3 and 4 minus j. Yep. So that the 2 minus 3 is minus 1. 4 minus j is that's 5j. Is that the same answer as we had before? Yeah? And then lastly, using the same method, C, Z2 minus Z1 is equal to 3 minus j minus 2 plus 4j. and looking at it like this, we've got 3 minus 2, and down the bottom, minus j minus 4j. Yep. Everyone agree? Three minus 2 is 1, and minus j minus 4j is minus 5j. Is that the same result as we got before? Yeah. So that method, having a go first through up a few problems, dealing with the positive and negative numbers. That method, with Paul's good memory from what he did last year, Ben might remember doing that too, is that cross multiplying, looking at that with the arrows going across, and eventually once you've done enough of them, you stop drawing the arrows in and you just write it out anyway. Okay, but just be careful with your positive and negative numbers, because quite a few people tend to make that mistake under pressure in exam as well. Okay, so that is addition and subtraction of two rectangular numbers. All right. So, multiplication of Cartesian complex numbers. Multiplication is achieved by multiplying out the brackets and using the fact that j squared is equal to minus 1 to simplify. Okay, I'm going to go through this one as an example, so I'll pick it up from there and write it out a little bit bigger. We've got 3 plus 2j. We're going to multiply that by 4 minus 5j. What do we do when we multiply out brackets in normal algebraic terms? What's the process to multiply out two brackets? If that was a plus b times c plus d, what do we do? A times c, we do a cross multiply, don't we? Do a times c, a times d, b times c, and b times d. All multiplies. And we do exactly the same here. So we do 3 times 4. 3 fours are 12. We do 3 times minus 5j. Minus 15j. Put it in the same colour. Minus 15j. We do 2j times 4 plus 8j, and we do 2j times minus 5j, minus 10j squared. All right? So that's the full multiplying out of the brackets. We can then gather together terms that are the same. That's just a constant. Okay, leave that one for a minute though. We got minus 15j's here, and we got plus 8j's there. What does that make altogether? Minus 7j. Okay. What we've got on the end here, let's just leave that one as 12 for a minute. Okay. What we got on the end here, we got minus 10. Do this in black. Minus 10 times j squared. What is j squared equal to? J is equal to the square root of minus 1. So j squared, this bit in brackets here, is equal to minus 1. So we can write this out as 12 minus 7j minus 10 times minus 1. Yeah, you've got minus 15 plus 8 is minus 7. Yeah, 12 has stayed on its own for a minute. But what is minus 10 times minus 1? Plus 10. So we can do 12 equals, I'm doing this all separately at the moment, minus 7j plus 10. That bit is equal to plus 10. Alright, so finally our resultant, or our answer, is 22 minus 7j. Right, take me through the first one then. What we've got is 1 minus 3j. I'm going to multiply that by minus 2 plus 5j. Take me through it. Jordan, put you on the spot.
Here, minus 2
equals minus 2 plus 5j plus 6j minus 15j squared minus 2 plus 11j yeah, because that bit is equal to minus 15 times minus 1, it becomes a plus 15 constant. Yeah, so the j squared term disappears. Alright, so the final answer, 13 plus 11j. Okay, and then the second one involves you taking the result of that and multiplying it by Z3. So we've got 13 plus 11j, and we're going to multiply that by minus 3 minus 4j. And the result of that is, someone else lead me through it. Ben, have a go. Minus 39, minus 52j, minus 33j, minus 44j squared. I'll put yeah. So you've done it all in one go. So that bit becomes a plus 44, doesn't it? Yeah. So minus 39 plus 44 is 5. Okay. So as a process to be gone through carefully, step by step. And the one thing to remember is j squared is equal to minus 1. Okay, and it becomes very useful in the division of Cartesian complex numbers, because we need to be able to get rid of all the j term in one part of the fraction. Okay, so what I'm going to propose we do, just 10 minutes early this week, let's go to a break now, and then we'll carry on with the division afterwards.